1, average velocity is defined as the ratio of which two quantities? Well, average velocity equals a change in position over the change in time. Technically, time elapsed. So average velocity is position over time. Number 2, average velocity is equal to the slope of a secant line through 2 points of a graph. Which graph? So anytime you do average, that's like a slope. Always think of it as a crappy derivative. So if you're trying to find velocity, you gotta take a derivative of what to get velocity? That would be position. So it's a position function. So average velocity on t is a little more explaining. T2, I guess T0, T1, if I want to do it correctly, is S of T1, it's just a slope, S of T0 over T1 minus T0. So the real answer is slope of secant line on the position function. So that's the answer, the position function. It's a little confusing, but average velocity, it's not the slope of a secant line. It's not a secant line through the velocity function. It's always the one above it. Because the idea is essentially you're taking a crappy derivative. So if I take a derivative of velocity, I get acceleration. But I'm asking about velocity. So you gotta take a derivative of position to get velocity. Can the instantaneous velocity be defined as ratio? Instantaneous is just a derivative. So like when they say average, you're doing a slope. Instantaneous, you're doing a derivative. It's tricky. Because so is a derivative defined as a ratio? Technically, no. I know we think, yes, it's rate over time, it's miles per minute or whatever, miles per hour. But really, the way you find, since it's instantaneous, you're taking a derivative, what is a derivative? The derivative is the limit of as t goes to t0 of this guy, s of t minus s of t0 over t minus t0. So technically, it's not a ratio, it's a limit of a ratio. So, no, it's the limit. Well, it'd be nice if I was just writing it. No, it's the limit of a ratio. So that's a tricky one. Next one, what's the graphical interpretation of instantaneous velocity at the moment t equals t0? Talked about, right? Instantaneous velocity is a derivative. And what's the derivative? It's the slope of a tangent line. At t0 on the position graph. So the slope of the tangent line on the position graph. Right, average means slope, so you're doing a secant line. Instantaneous means derivative, so you're doing a tangent line. What's the graphical representation of the following statement? The average rate of change, that's what ROC means, approaches the instantaneous rate of change at interval x0, x1 shrinks to x0. This is a classic representation of how you take the slope of a single point. This is the thing where we're taking the slopes of lots of secant lines, and we're going to take a limit of them to find the slope of a single point. So that's all that's going on here. We're going to use the slopes of secant lines on the position graph that approach the tangent line to approximate the instantaneous rate of change. That's what that is. So that's all it is. It's like when we first learn how to take a derivative, and we're like, hey, how do you take the derivative? How do you take the slope of a single point? Well, you don't. You take the slope of 2 points on a line, and then you go a little closer, and you go to, that was a bad. And you go a little closer, and a little closer, and a little closer, and then you take the limit. That's kind of the idea. That's what's going on here. Oh, finally problems. A ball is dropped from a state of rest at t equals 0. The distance traveled after t seconds is given by this formula, s of t equals 16t squared. how far does the ball travel during the time interval of 2 to 2.5? So if you want to figure out how far the thing travels between 2 and 2.5, well, let's figure out first how far it travels in 2.5. Then we figure out how far it travels in 2, and then we subtract. That's all it is, right? Figure out where you're at 2, figure out where you're at 2.5, subtract them. So if I do this, I'm going to get 16 times 2.5 squared minus 16 times 2 squared. Put that into our calculator, and we get 36 feet. Go. Compute the average velocity over 2 to 2.5. So remember, average velocity is just slope. We see the average slope. Now the thing is it slope of velocity or slope of position? It's slope of position. It's always slope of the one above it, right? How do you get velocity? You take the derivative position. So we're just taking a crappy derivative. So we're going to do slope equation. 2.5 minus 2, and then s of 2.5 minus s of 2, right? Just normal slope. So that gets me, at the top I already know 36 did earlier, and this is 0.5. 36 divided by 0.5 is like 36 times 2, so 72 feet per second. Notice the units, top here is feet, and the bottom here is time. And it is seconds. I just guessed earlier. And we got that, 72 feet per second. Next one. A stone is tossed in the air from the ground level with an initial velocity of 15 meters per second. Its height at time t is given by this. So this is our position function in meters. Compute the stone's average velocity over the interval 0.5 to 2.5 using your graphing calculator to sketch h of t, indicate a corresponding secant line on the graph. Okay. So the first part just wants us to find the average velocity. And again, we did that before. It's just slope. Slope it, and then you have to use. So average rate of change, average velocity, right? Average velocity, velocity average. It's just the slope. So we're going to do 2.5 minus 2, and then h of 2.5 minus h of 2. Again, when you're trying to find average velocity, you do the position function. It's always the one above it. Or if you want to think, how do I get velocity? You take a position and a slope. And average is a crappy derivative. It's a slope version of it. Anyway, put those values into our calculator. We get 0.6 over 2 or 0.3. And again, this is meters. This is seconds, so meters per second. Then they want us to graph this on our calculator. So if we graph this on our calculator, we get a graph that looks kind of like this. And they want the secant line at right here. This is wrong, by the way. I did the math in my head. There we go. I did that, so it's tracked in my head already. So 0.5 is over here. 2.5 is over here somewhere. And they want the secant line through these points. And there we go. That's the idea. Now that's not to scale, but that's the general idea of what's going on here, right? We're finding the slope of the secant line right there. With an initial deposit of $100, the balance in a bank after T years is given by this. What are the units of rate of change? So just what are the units? Again, not even like take the derivative. Just what are the units of rate of change? Well, look where we start off at. We start at dollars, right? That's our original function. And then when you take the derivative, you divide by the time. So our time here is years, so dollars per year. So that's the rate of change. So how do you find the rate of change? You take the derivative, you take the slope, right? So it'll be that over that. Find the average rate of change over this. So average rate of change is over for just slope. So we're just going to do f of 1 minus f of 0 over 1 minus 0. Again, and this would be in dollars. This would be in years. So you just plug it in. So the 1 minus 100. 1.08. So the 0 over 1 minus 0. Put in your calculator and you get $8 per year. So that's average rate of change. You get about $8 per year for your deposit. Number 8. The total distance traveled by a particle at time equals t is given by this. Compute the average velocity over time, interval 1, 4. Find instantaneous velocity at t equals 1. So first, let's do it. They want the average velocity. So velocity average, right? It's just the slope. Let's do, what are we doing? 1 and 4. So just 4 minus 1 over s of 4 minus s of 1. As we talked about, average velocity, use the one above, use position. So we have this, we're just going to plug this in. So 4 cubed plus 4 minus 1 cubed plus 1 all over 3. So 64 plus 4, 68 minus 2. So 66 over 3, which equals 22. So that's our average velocity. They don't give us any units, so I'm just going to leave it average velocity from 1 to 4. Or from 1 to 4. Anyway, that's our average velocity. Now they want the instantaneous velocity. Instantaneous velocity, that's just the derivative. And derivative, that would be 3t squared plus 1, and then you plug in 1. Which should give me 4. So that's instantaneous velocity at t equals 1. So there you go, right? Average velocity slope, instantaneous velocity derivative. So all these, it was find the instantaneous velocity. So we're just going to take a derivative of all of them. So p prime of x is equal to 8x. So p prime of 2 would equal 8 times 2, which is 16. Next one, y prime. Well, before I do that, I got to rewrite it. So just y, I'm just going to rewrite y first. So x plus 2 to negative 1. I could do quotient rule if I want, but this is a little easier. Just bring it all up, make it a negative 1. Now it's a chain rule. So that makes y prime. Bring it down, subtract 1 off. Negative 1, x plus 2 to the negative 2 times the derivative of the inside, which is 1. Our little chain rule, bring it down, subtract 1 off, do the inside alone, times by the derivative of the inside. In this case, we got lucky, it's just 1. Okay, so now y prime of 2. We're just going to plug 2 in. Let me make this a little bit easier for myself. Move it to the bottom. Plug it in. So you get negative 1 over 4 squared, which is negative 1 over 16. So there you go. 12, same idea. Take the derivative. First, I gotta rewrite this. So the derivative is gonna be 1/2 3t plus 1, subtract 1, chain rule. Times by derivative of the inside. Right, so brought the 1/2 down, subtracted 1 off. Leave the inside alone, times by derivative of the inside. So we just essentially get 3 over 2 times 1 over square root of 3t plus 1. Now we'll sub in 1. You get 3 over 2 times 1 over square root of 4. So 3 over 4. So there we go. Next, the height in feet at time t equals 0 of a small object oscillating at the end of a spring is given by this. That's the height. Calculate the weight average of a small weight, Calculate the weight's average velocity over the time it rolls 0, 1, 3, 3, and 5. Velocity is just slope. So 0, 1, we're going to do 1 minus 0, and then h of 1 minus h of 0. So it's going to be, let's see, playing the formula. 0.5 cosine of 8 minus 0.5 cosine of 8 times 0, which is just 0, over, well, it's cosine of 0. Cosine of 0 is actually just 1, over 1. So I just get 0.5 cosine 8 minus 0.5. And that's all I could do. Units, it is feet, seconds, and this is it, right? So this will be feet and this will be seconds, so feet per second. So there we go with that one. Find average velocity 3.5, so same idea. Just 5 minus 3, h of 5 minus h of 3. So I get 0.5 cosine of 8 times 5 is 40, minus 0.5 cosine of 8 times 3 is 24, all over 2. There we go, unless you want to make it a little nicer. If you want to make it a little nicer, I can pull out the 0.5, and I get cosine of 40 minus cosine of 24, all over 2. That's the same thing as 1/2. So that means the 2 goes to the bottom. So you get this cosine of 40 minus cosine of 24, all over 4. That's as far as you go. You can't do anything else. Remember the 4 and the 40 don't cancel out. This is stuck. Same thing here. So that's all you could do. Units, again, will be feet per minute, I believe. That we have last time. Feet per second. So there we go. Okay. Last page. The graph below represents the position of moving particles as a function of time. Do instantaneous velocities at t1, t2, and t3 and t3 in A form an increasing or decreasing sequence. So remember, instantaneous velocities are the slope of a tangent line. Right, so at t1 we have a slope. That's our slope right there. At t2 we have this slope. Now you gotta decide, is that slope higher or lower than this slope? Like if you took the slope of this, you might get like, I don't know, 3. If you take the slope of t2, it's a little bit straighter. So that means it'll be something like, I don't know, 2. And then you take the slope of t3, that's even more straight. So your slopes are like decreasing. So S prime of t1, that's this guy. That's a steeper slope than the rest. So that's the biggest. Then it becomes S of t2. Right, that's this one. And the least steep would be this guy. My first one, by the way, was off. First one is this one. That's the most steep. Then this one, so the next one. Then this one. So slopes are decreasing. They're still positive, but they are decreasing. Right, so they're still positive slopes, they're just getting smaller as we go to the right. This particle speeding up or slowing down in A. So that's a little tricky. So remember, to speeding up or slowing down, that's all you want to do is check velocity versus acceleration. Same sign means you're increasing. Different signs means they're working against each other. And you're slowing down. So, what's going on here? Look at our velocities. They're positive. They're all positive, right? And they're, like I said, they're decreasing, but they are positive. They're positive velocities. So my velocity is positive. My acceleration, though, right? See how it's decreasing? The slope is decreasing. Remember, slope is derivative. That's all slope is. It's like a crappy derivative. Slope means derivative in this case. So my velocities are positive. They're going smaller, but they're positive. The slope is decreasing though. So that means the derivative velocity is negative. So my acceleration is negative. Right? So my velocity is greater than 0. My acceleration is less than 0. They're different signs, so they're slowing down. Velocity and accel have opposite signs. So there we go with that. There's particle speeding up or slowing down in B. So we have to kind of go through the same sequence in B. Look at my slopes. So my velocity is positive. And look how it's getting steeper actually. In this case, we don't actually have times, but it's increasing. Velocity is increasing. Right? It's going higher and higher. So that means my acceleration is positive. So they're both the same sign. I don't care if they're both positive or they're both negative. It just matters that they're both the same sign. Right? Just by looking at these guys, these are positive slopes. And they're getting steeper and steeper. So that means it's increasing, which means the acceleration, the derivative velocity, is positive. All increasing means is derivative positive or negative. That's all it means. So in this case, it's speeding up because velocity and accel are the same sign. Okay. Next, the graph below represents the position of a particle at a function of time. Match each graph with one of the following statements: speeding up, slowing down, speeding up, then slowing down, and speeding up. Okay, so look at this one. It's like your car, right? This would be slowing down. Like you're going really fast, but then like you're leveled off. So this is slowing down. You can also look at it as it's increasing. So like if you look at my slope is positive, but it's getting less steep. It's like going concave down. So that's why it's like velocity is positive, but acceleration here is negative. If you look at this one, it's like speeding up, but look at that curve, you're getting faster, but then you're starting to slow down. Then you do the opposite, you're slowing down. So speeding up, and slowing down. Like here, this like it's all increasing, so it's all velocity is all positive. But then like look at the slopes, it's getting steeper, and right here it's getting less steep. So it changes. This one, you start off really fast, but then you start like leveling off. So you're slowing down to start off. Then over here, you're getting faster again. So it's going like this. So speeding up. And this one's just speeding up the whole way. It's just going up the whole way. And the last one, I forgot to erase the answers. The answer's right there. It's B. Done. Which graph below has the following properties for all x? The average ROC. The average rate of change is greater than the instantaneous rate of change at x equals c. So it wants to know, like, when you draw a tangent line, it should be steeper than the if you draw this secant line, it should be steeper than the tangent line. So if we have this point right here, that's the secant line, and this would be my tangent line. So right, as you can see, the tangent line is steeper than the rate of change. But on this one, if you draw a line and you draw a tangent line, the slope is bigger than the tangent line. So it's that one. Anyway, that's the work.